Good morning to everyone. Thanks for the invitation. Can you hear me well?
Yeah.
Okay, so please, Idris, if you can move to the presentation mode, probably. What we are seeing now is anyway, maybe. I don't see the screen with the slides running, but maybe it's coming. Okay. What I will, okay, sure. What I will present briefly is some of the results of this European project called Africa-Europe Collaboration on Bioclimatic Buildings for the 21st Century, coordinated by myself and Professor Silvia Erba. Idris, we have a, okay, great. Yeah, so yes, I'm professor in building physics at the Department of Architecture and Urban Studies at Politecnico. Slides are progressing, but maybe slowly. I see always the same one. Yeah, that's the difficulty of being far away. But also we are saving a lot of CO2 by not traveling. So in any case, this project is a project which involves a number of countries in Europe and in Africa, both academics and ministries, and so I start my counting time, and also practitioners, architects and building construction. Okay. Yeah, so I see some difficulties. So maybe I continue without the slides to gain time, and then we go to the slides. One of the ideas is definitely to exchange knowledge between Africa and Europe, also learning from the recent wave of African architecture, new young architects reviving vernacular architecture and local materials. Okay, maybe now the slides are on. Okay, great. And one of the goals is to design for the future weather. For this, we need to anticipate what will happen in the next decades, rather than using as input for the simulation and calculation weather data which are referring to the past, as it happens mostly today. So this is one thing. We need this description of the future weather, accurate or approximate, and available publicly and certified publicly. Idris, if you can go on with the slides. Okay. I guess for those watching, I don't know if it's possible to make my video smaller and the slides, or even take away my video. I see the slides very small. And this will help also the next speakers, I guess. So one other objective of the project is to promote the use of a common language, which is anyway required by international standards. One common language which can be used is the language of the international standard 52000, very recent. And one indicator that we should use in this effort to promote bioclimatic architecture is the indicator energy needs for heating and cooling. For example, the energy need for cooling, which we should see on the screen now, but I see it very small, is describing the quality of the building fabric per se to maintain temperature inside in the indoor space. And it is the energy needed to keep the indoor space at a certain temperature for a certain time. And it is the difference of the input of energy into the space, for example, via solar radiation through the windows, internal gains by people, minus what we can export out of the building, for example, during the night, washing the space with cool air from outside. The difference, what remains, is what is the energy need, which needs to be taken out via passive or active systems. Together with the energy need for heating during the heating season, these are the two parameters which describe the building envelope from a physical point of view, objectively, without all the complications and uncertainties which are connected with the use of other indicators like primary energy, total or non-renewable. Let's go on to the next slide. We missed the part of this one, but by the way, I can try to have my slides also here. Okay. No, this is the end. So there are some building codes which already use these indicators, energy needs for heating and cooling. For example, in Morocco, the building code limits the energy needs for heating or cooling. So it focuses on the envelope, as it should be, for a number of reasons. In Switzerland, it is mandatory to have a low value of energy needs for heating, and it is mandatory to have solar protections, minimum thermal mass, and only after that you have the permission to install active air conditioning if still needed. There is another parameter which is called the net zero energy or net zero CO2 balance over a year, which is sometimes used in a misleading way. If you do a virtual balance over a year, you can get zero, making the difference of the energy the building uses minus the energy, renewable energy generated at the building site over a year. But in the different months, the balance is not there. And so you need to have seasonal inter-storage. You store energy today and use it 6 months later. And this requires a lot of materials, land, and implies losses, which in many cases are not counted into this paper balance. There are ways to, please go on to the next, to correct this. For example, in the Italian legislation, the energy balance on primary energy is done month by month rather than over a year. And if calculation would be available to calculate hourly, then the balance could also be done hourly. Okay, but the real solution to this is to this unbalance is to reduce the energy needs. So if all these bars are much lower, they can be 90% lower, then also the unbalance is 90% lower, and the storage to be built is 90% smaller. So the real solution is to have a building fabric which reduces strongly the energy needs. Please continue to the next. We are already, in fact, on the next with the corrections that I was proposing. Calculate on monthly or hourly basis. And in fact, what's needed is to reduce the energy needs with a very good building envelope. Next again. Okay. And also we need to use comfort indicators. What is done to define comfort is to do simultaneously measurements of temperature, air velocity, radiant temperature, interview people asking them, how do you feel at this time? And requiring an answer standardized in this scale from cold to hot. Tens of thousands of these interviews have been done and are collected now in the ASHRAE Comfort Database 2nd, published in 2018. We have participated to this work. And in Africa, we will add new data with new measurements we are running now under the project ABC21. Please continue. One important parameter is air velocity that's shown by these measurements and interviews. So we knew from experience that if we have air velocity indoor, the comfort zone goes to higher temperatures. So you can be comfortable at 28 with air velocity as much as at 24 with no air velocity. So this is an example of a building in La Réunion where there is, for example, in the classrooms at the upper floor, cross ventilation to provide this air velocity and ceiling fans. At the lower floor offices, they have available both cross ventilation, ceiling fans, and a bit of air conditioning, and they can mix these three ways to achieve comfort, even air conditioning and air conditioning at high, let's say, keeping the temperature relatively high, and air velocity. This seems to work well, and the response of the occupants is documented in the paper you see below. Please, let's proceed to next one. So this is crystallized in the norms now in a very explicit way that allows to do calculations, include easily. We will not go into details. You find the details, for example, in the ASHRAE 55 or the European legislation. And again, the analysis of the database shows that, please, next one is good. Okay, examples where people have been interviewed also is this large space, also large spaces can be, let's say, made comfortable via the use of large ceiling fans as this large space, or this classroom by Francis Quéré, a winner of the Nobel Prize in 2022, Nobel Prize for Architecture, Strixer. There are ways to calculate how to distribute velocity with the ceiling fans for designers. Let's go to next one. Cross ventilation is included in the design of many buildings of the new wave or African architecture, like this one from Vincent Quéré, this school. So ventilation for daytime comfort, for night cooling. Let's go on. For example, these residential buildings have been designed with a shallow depth so that cross ventilation is actually possible, and the surroundings are designed for no cars at surface, no noise, possibility to open at night without disturbances. This is in La Réunion. Let's go on because time is running. That's the last one. or almost. So then we can measure, document what's the comfort achieved. For example, in one case studies of the ABC21 project, we have a building residence with 25 centimeters external insulation, high thermal mass, natural ventilation. It's in Sicily, so a warm climate for Italy. We see the blue line is external temperature, which goes up to 40 degrees Celsius in certain days. The green line is the indoor temperature with no air conditioning active, so only with natural ventilation and the thermal protection. And the indoor temperature oscillates between 25 and 26, 27 maximum. So within the comfort zone and the energy need for heating and cooling is 90% less than in a conventional building. Let's go on to the last one. So the lines, the comfort lines you have seen that were changing over time are described via the adaptive thermal comfort model, which again comes from that big tens of thousands of interviews where the model says very simply that indoor comfort requirements, temperature required by people, grows with the external temperature. So the higher the temperature outside, the higher the required temperature inside, which helps to design passive buildings rather than keeping a strictly 23 degree constantly, as sometimes we do. Go to the last, please. So adaptation and mitigation in buildings are probably the same thing if we do good envelope. Good envelope helps to cope with extreme events, to give thermal safety, and to achieve very low energy needs for heating and cooling, so low CO2 emissions. Documents available on the website. I close. I'm sorry that with this complication, it has taken probably some minutes more than planned. Thanks a lot.
Thank you very much, Lorenzo, for